All right, everyone, welcome. Have you ever really stopped to think about how the thoughts buzzing around in your head actually turn into the words that come out of your mouth? It's an incredible process. Today, we're going to dive deep into the neuroscience of language. We'll break down exactly how our brains pull off this amazing feat, and we'll cover all the core concepts you'll need to absolutely nail your exam. So, here's our game plan. We're going to start by busting a huge myth about being left-brained or right-brained. From there, we'll pinpoint the exact anatomy of language, look at what happens when things go wrong, and check out the evidence that proves it all. And to finish, we'll get into some of the really cool nuances that tie the whole picture together. Okay, first things first. There is a massive pop psychology myth out there about how our brains work, and I guarantee you've heard it 1,000 times. It's time we separated that from the actual scientific reality. You've all seen this, right? Maybe you've even taken one of those online quizzes that tells you you're a super logical left-brainer or a wildly creative right-brainer. Well, the truth is, that's a huge oversimplification. It's just not how it works. While our brain hemispheres do have different specialties, nobody is exclusively left-brained or right-brained. Your two halves are in constant communication, working together on pretty much everything you do. So the correct scientific term you need to know is lateralization, and this isn't about one side being better or more dominant. Think of it more like an efficient division of labor. By having specialized regions, the brain avoids duplicating its efforts and can process information way more effectively. And here are some fantastic, concrete examples of that division of labor. For the vast majority of people, the left hemisphere handles the nuts and bolts of language, the vocabulary, the grammar, the sentence structure. Meanwhile, the right hemisphere is the expert in things like spatial tasks, recognizing faces, and, this is super important for communication, interpreting the emotional tone of speech. That's a concept we call prosody. Okay, so if language is mainly a left hemisphere job, where exactly in that left hemisphere is the magic happening? Let's zoom in and meet the key players in the cortex that run the show. Our whole modern understanding really got started in the 19th century, thanks to two absolute pioneers. First up was Pierre-Paul Broca. He was a French neurologist studying patients who could understand language just fine, but couldn't speak fluently. He was the first to connect a specific function, producing speech, to a specific part of the brain. A little later, Karl Wernicke, a German neurologist, refined this by finding patients with the exact opposite problem. They could talk up a storm, but they couldn't understand what was being said. And their discoveries gave us this foundational classic model of language anatomy. You've got Broca's area, up in the frontal lobe, which is basically the speech production factory. It plans the motor movements for talking. Then you've got Wernicke's area, back in the temporal lobe, which is the comprehension center. It's crucial for figuring out the meaning of words. So, we've identified these two critical hubs for language. Now, what happens when they get damaged? Maybe from a stroke or a head injury? The result is a set of language disorders known collectively as the aphasias. And because these two areas have completely different jobs, damage leads to two very distinct types of aphasia. Damage to Broca's area results in an expressive or non-fluent aphasia, and damage to Wernicke's area causes a receptive or fluent aphasia. Now, that difference in fluency, that's the absolute key thing to remember for your exam. Let's really break down the differences here. A patient with Broca's aphasia speaks with a ton of effort. It's halting, the grammar is all over the place, but, and this is critical, their comprehension is mostly fine. They know what they want to say. In stark contrast, someone with Wernicke's aphasia speaks fluently with normal rhythm and everything, but the content is often a jumbled, nonsensical word salad, and their ability to understand language is severely damaged. This quote from a patient really brings the experience of Broca's aphasia to life. You can just feel the frustration, can't you? He knows exactly what's wrong. His arm and his speech are no good. But actually forming that complete grammatical thought is an incredible struggle. The idea is there. The words just won't come out right. Now, compare that to this example. The speech just flows. The rhythm, the intonation, it all sounds perfectly fine. But the words themselves, they're meaningless. Repusor, repusuration, those aren't real words. This is that classic word salad, a fluent stream of language that's completely incomprehensible. It's a perfect illustration of a total breakdown in meaning. The work from Broca and Wernicke was absolutely revolutionary, but you have to remember, it relied on autopsies. They could only correlate a patient's symptoms with brain damage after they died. So the next big step was, how did science prove all this was happening in living, breathing brains?
I mean, think about it. That was the critical puzzle to solve. If you really want to prove that the left hemisphere is the language specialist, you somehow need to find a way to isolate it, to talk to just one hemisphere at a time and see what happens.
And the definitive answer came from these incredible studies on split brain patients. These were people who, to treat severe epilepsy, had their corpus callosum, that's the huge bundle of nerves connecting the two hemispheres, surgically cut. So researchers could flash a word to their left visual field, which sends the information only to the nonverbal right hemisphere. And what happened? The patient couldn't name the object. Why? Because that information was literally trapped on the right side. It had no way to get across to the language centers on the left. It was the ultimate, undeniable proof of language lateralization. And you can really see the incredible evolution of our scientific toolkit over time. We went from those early autopsies to actually stimulating the brain during surgery, to the WADA test, where they'd briefly put one hemisphere to sleep with an anesthetic. And today, of course, we have amazing non-invasive tools like fMRI that let us watch the language areas light up in real time. And these new tools have confirmed the classic model, but they've also shown us there's a lot more individual variation than we ever thought. Okay, let's get into our final section. We're going to move beyond that simple Broca-Wernicke model. These are the crucial details that will give you a much richer, more complete picture of how language really works in the brain. This is the stuff that separates a good exam answer from a great one. So just how common is this left hemisphere dominance for language? Well, the number to remember is 97%. That's the percentage of the population where language is primarily a left hemisphere function. And what's really fascinating is that this number includes the majority of left-handed people. So that old idea that being left-handed automatically means your language is in your right hemisphere is, for the most part, simply not true.
So if the left side is doing all the words and grammar, what's the right hemisphere doing? Is it just taking a break? Absolutely not. It's handling something incredibly important: prosody. That's the emotional color, the rhythm, the intonation of speech. It's not what you say, but how you say it. Damage here can cause something called aprosodia, where a person speaks in a flat, robotic monotone, unable to convey any emotion with their voice, even if they're feeling it inside.
Now, this next point is fundamentally important. It gets to the very core of what these brain areas do. Studies of deaf individuals who use American Sign Language and then suffer a stroke have found something remarkable. If the damage is to their left hemisphere's Broca's or Wernicke's area, they develop a signing aphasia that looks just like the spoken versions. This is powerful, powerful proof that these brain regions aren't just for sounds or for moving your mouth. They are specialized for something much more abstract, for symbolic communication itself. And finally, let's talk about timing. Does it matter when you learn a language? You bet it does. This classic data shows what we call the critical period for language acquisition. As you can see, people who learn a second language before about age 7 have a really good shot at achieving native-level fluency. After that, the window starts to close, and it gets progressively harder. It's a perfect demonstration of the incredible plasticity, the sponginess of the young brain. And that brings us to our final big picture question. We've established that the brain's incredible capacity for language is really a capacity for symbolic communication. And that leads to a profound thought that connects all of this neuroscience back to evolution. Where did this ability come from? And are we the only species on the planet that has it? It's a massive question that researchers are still working hard to answer today.